Hello everyone. So today I have an extremely amazing problem for you and we're going to be discussing about counting. Now this is obviously not a very simple question on counting, as you will get to know soon. And it's not about maybe just simple principles of countings that we see in combinatorics. It's actually a little bit trickier than that. And you're going to see how we're going to form certain cases, maybe analyze certain ideas, how basically casework works in most of these problems. So yeah, let's begin and hope you have fun. So this is the problem number 18 from the AMC 12B in 2014. And in this video, we're going to be learning about counting and casework in Maths Olympiads. A neat observation, which I'll talk about later. Then we have book sessions with the AMC, and at the end, a similar but challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so maybe I can just zoom in. Okay, so they are saying that the numbers 1, 2, 3, 4, and 5 are arranged in a circle, right? And arrangement is bad if it is not true that for every n from 1 to 15, one can find a subset of the numbers that appear consecutively on the circle that sum to n. Okay, arrangement that differ only by rotation or reflection are considered the same. How many different bad arrangements are there? Now, let's just take a moment to kind of like understand what they're trying to tell us. They're telling us an arrangement is bad if it is not true that for every n from 1 to 15, one can find the subset of the numbers that appear consecutively in the circle that sum to n. There's a lot of things going on around here, so let me just make it a little bit simple. So whenever in any question really, if you have this bad, not true, a lot of these negations, and what you do is you just convert it to good. Okay, so if they are saying the arrangement is bad if it is not true, then let's just look when is the arrangement good. Right? So the arrangement is good when it is true, okay, when it is true that for every n from 1 to 15, so n is basically from 1 to 15, one can find a subset of the numbers, subset for example any kind of combination of these numbers from this set, subset of the numbers that appear consecutively on the circle that sum to n. So let's just take an example. So if we have, let's say n is equal to 7, so if we have on the circle containing 5 elements, let me just demarcate that like this, and if we have, let's say 5 and 2 consecutively, then this is good, right? If we have, let's say again, just let me draw this, if we have, let's say 4 and 3 consecutively, this is also good, right? If it does not have that, it is bad, right? So for example, if I am able to figure out a circle, which you will eventually find, let's say the sum of any two consecutive elements, any of these two consecutive elements is not 7, then it will be bad. So not 7 is bad. And this is obviously for n is equal to 7. And in total, we need to, what's the question asking? We need to find the total number of such bad arrangements from n is equal to 1 to 15. Right, both inclusive actually. So yeah, that is essentially what they are asking us to find. So how shall we proceed with this? Well, now that we've understood the question, we can essentially see that the numbers n is equal to 1, 2, 3, 4, and 5 will always be good, right? And you know, why is that true? Because for example, these numbers in itself, for example, in a circle you have 1 over here. No matter what the other 4 are, you're always going to have this 1. And what is the sum of this one? It's obviously 1, right? So the sum is 1 for an element that is just itself, so it is obviously good, right? Similarly, if you have 2 right by itself, does not matter what the arrangement of the other 4 elements are, it is good, right? The sum of 2 is good, essentially, if you get what I mean. Similarly, if we have, let's say 3 by itself, it is also good. No matter what the arrangement of the other 4 are, it is good. It's a good arrangement. You have number 4, it by itself is good, and similarly number 5. So these numbers on their own merit, if that makes sense, are good. Right? They're all good arrangements. So we do not need to check for these 5. Now using a similar argument, so for example, n is equal to 1, 2, 3, 4 and 5. If I cancel 5 from this, okay, if I just ignore that, we are going to have 4 elements that sum to 4, 7, 9 and 10. So again, for n is equal to 10, we do not need to check this because this will be good for any arrangement. Right? All we need to do is really just remove the 5. For example, let me just give you an example. For example, these are the 5 elements. You have, let's say, 1, 3, 4, 2, 5. Just random arrangement. Now, if I just remove this 5, what's the sum of the other 4? 4, 7, 9 and 10. So any arrangement of this is for n is equal to 10 is always going to be good. Right? Similarly, if I remove a 4, I will get n is equal to 5, 8, 10, 11. Similarly, if I remove a 3, I'll get n is equal to 12. If I remove a 4, I'll get, if I remove, let's say 2, right, I'll get n is equal to 13. If I remove 1, I'll get n is equal to 14. And if I don't remove anything, I'll get n is equal to 15, right? All of these 5 numbers, when you add them up, you'll get 15, right? So they themselves essentially sum to 15, and n is equal to 15 will always be good. So what things can we draw from here? So n is equal to 1, 2, 3, 4, 5. Okay. After that, we have 10, 11, 12, 13, 14 and 15 are all good for any arrangement. Right? They're all good for any arrangement. No matter how you arrange them, they are always going to be good. How you arrange the numbers, essentially. So we only need to check for n is equal to 6, 7, 8 and 9. Right? So yeah, that definitely kind of simplified our process a little bit, and we have something to work with, and now we can actually go on to form some cases. Instead of 15 numbers working with their cases, we have only 4 numbers. So let's just first consider the case where n is equal to 6. And just to remind you, we need to find the number of bad arrangements. So n is equal to 6, so no 2 numbers or no 3 numbers should not sum up to 6. No subset from this 1 to 15 consecutive subset should sum to 15. Right? So how are you supposed to find 6? Well, 1 and 5 is 6. 2 and 4 is 6. 1, 2 and 3 is also 6. And you can really just check there are no other ways to form 6 out of the numbers 1, 2, 3, 4 and 5. Right? These are the only 3 cases. So I cannot have on this circle 1, 2, 3, 4, 5. I cannot have 1 and 5 together. Right? So let's just put 5 here. I cannot put 1 over here and over here. I cannot put 1 over here and over here, right? So I need to put it over here, and really it's immaterial. You can take it wherever you want. Let me just take it here. And I'll actually tell you why it does not matter later on. But now we cannot have 2 and 4 together. We cannot have 1, 2 and 3 together. So well, what shall we do? So if I put 2 over here, right? I cannot have 3 over here, so I have to put 3 over here. Right? I cannot have 3 in this place because then 1, 2, 3 would be consecutive. I have to put 3 over here. And what is left? 4. But this is one arrangement where you do not have 6. And you can just check 1 and 5 are separate, 2 and 4 are separate, and 1, 2 and 3 are also separate. So this is actually a valid condition. Now, here the question arises, can you form any other arrangements? Well, the answer is pretty much no, because any other arrangement that you find will be a mirror reflection, and they have specifically told us not to consider the mirror reflections, right? So arrangements that differ only by rotation or reflection are considered the same. So essentially, this is what I was referring to earlier, that if instead of putting 1 over here, I would have put 1 over here, let's say, then that would essentially be nothing but a reflection, right? So we do not need to consider that. So for n is equal to 6, we have one bad arrangement. Now, let's move on. Let's move on to n is equal to 7. Now, again, how can you form 7? 7 can be formed by 2 and 5. 7 can be formed by 4 and 3. 7 can be formed by 4, 2, 1. 4 plus 2, 6 plus 1, 7. So again, I need to take this circle. And I cannot have 2 and 5 together. I cannot have 4 and 3 together. And I cannot have these 3 numbers together. Right? So let's just take, let's just take anything, right? Let's just take maybe 3 over here. Right? Now, again, using the same reasoning, 4 can either go over here or over here. Right? 4 can either go over here and over here. Again, I can just choose anyone really. I'm sorry, not over there actually. It cannot go over here. So, Yeah, so 1, 2, 3, 4, and 5. So yeah, it can go over here or it can go over here. Right? And again, let me just redraw this actually, so you get a better picture. Okay. 1, 2, 3, 4, 5. So if I put 3 over here, I can put 4 in 2 places. And which are these 2? I can put this over here, or I can put over here. Again, just you can choose anyone really. Now what do we do? Now we have 3 and 4 separate. I need to put 1, 2, and 4 separate. So for example, if I put 1 over here, 2 cannot go here, 2 has to go here. So that means 5 has to go over here. Now let's check this arrangement. We have 5 and 2 together, so this does not work. So does not work. This is a good arrangement, right? Again, let me just take the case. So I had 4 over here. I cannot put 1 over here. I have to put 2 over here. 1 cannot go here because then you would have 1, 4, and 2. So 1 has to go here. And the remaining number is 5. Now let's just see again. Do we have 2 and 5 together? No, we don't. Do we have 4 and 3 together? No, we don't. Do we have 1, 2, and 4 together? No, we don't. This 3 is coming in the middle. So this is another bad arrangement. And again, even for this scenario, any other really combination that you can find will just be a reflection that you can actually test it out. So for n is equal to 7, also we are going to have only one such arrangement, unique arrangement in a way, right? N is equal to 6 and n is equal to 7. Now here, a really important thing is to actually see if n is equal to 6 and n is equal to 7 are kind of the same or not. So the way to check that is, so we do not want them to be mirror reflections of each other, right? So we have here 5, 1, 3, 2, 4. Let's just see if that is unique. We had 5, 1, 3, 2, 4. Here we have 5, 2, 1, 4, 3. 5, 2, 1, 4, 3. So of course they are clearly unique. So till now we have 2 solutions. Now here is something where you can probably analyze a little bit. So we have 15, right? Total number is n from 1 to 15. And so for example, if there is a good 7, what does that mean? Let's say 5 and 2 are consecutive. So there has to be a good 8. Why? You just remove this. So for example, 1, 2, 3, 4, 5. If you have a good 7 consisting of, let's say, 5 and 2, let's say, or 4 and 3, or really whatever the combination, what will be left? Something like this. Something like this will be left, right? You can just mix up these 3 numbers, 1, 2, and 3. But essentially, this will be the combination. And what would happen over here is if I just don't consider this, what would these 3 are also consecutive, right? These 3 are consecutive numbers. And what is the sum? 3, 5, and 6, right? Sorry, I made a mistake actually. This should not be 2. This should be 4. So the sum would be 8. Yeah, now it makes sense. So the sum would be 8. So if we have a good 7, then automatically means we have a good 8. If we have a good 8, then automatically means we have a good 7, right? Because these 2 numbers, they sum to 15. So we have a good A, we will also have a good 15 minus A. Now using a similar kind of argument, if we have, let's say, no 7, we will have no 8. And let me just prove that to you. So for example, what are the ways to find n is equal to 8? Let's just analyze this if you want. So what are the ways to find n is equal to 8, right? 8 can be 5 and 3. 8 can be 5 and 2 and 1. And 8 can also be 4 and 3 and 1. Now that's great. Because now again, let me just draw the diagram. So I can put 5 over here. I can put 3, again, any over here. 5 and 3 cannot be together. Now what else can we do? Let's see. So 5, 2 and 1. So and 4, 3 and 1. So really, well, 4 can come over here, let's say. Let's consider the case where 4 is over here. 1 cannot come here, 1 has to go here. The remaining number is 2. But then the problem here becomes that 5, 1 and 2 are together, which we do not want. So let me erase that. 4 over here does not work. If 4 does not work, then 1 has to be over here. If 1 is here, 4 cannot be here because then 1, 3 and 4 would be together. 4 has to be over here. 2 has to be over here. Now let's analyze. 5 and 3 are separate. 5, 2 and 1 are separate. 4, 3 and 1 are also separate. But my friends, here if you actually check the arrangement, how do you check the arrangement? Just see the order. It is 5, 1, 3, 2, 4. This was for n is equal to 8. And if you actually see for n is equal to 7, what we had received, it was 5, 1, 3, 2, 4. So again, both of these are actually same. 5, 1, 3, 2, 4 and 5, 1, 3, 2, 4. So actually n is equal to 7 and n is equal to 8 are reflections of each other because of the concept of a and 15 minus a that I talked about earlier. So similarly for n is equal to 9, you would again get a reflection. You can really check that. So essentially the total number of bad arrangements are 2. Total number of bads are 2. And yeah, that was the answer. So this is definitely a little bit of a tricky problem, and it's not easy to analyze this in the exam. You have certain exam pressure, you have all of these situations that are going on in your head in the exam, but it is very important to kind of like make the cases quite properly, quite neatly, so that you really don't miss out on anything. There are a lot of things that can go wrong in this problem. You might miss out on certain cases, you might miss out on certain combinations that may sum up to n is equal to 7, n is equal to 8. It's really easy to miss that, and it's really easy to consider this and n is equal to 7 as unique combinations. Right, so in that case, if you do not actually check that, you would report the answer as 4, and which would be incorrect. That's a very important thing to keep in mind. So yeah, I hope you learned some very important lessons from that. So here's some book suggestions for the AMC. Mathematics can be fun, mathematical circles, algebra can be fun, excursion mathematics, challenges and theories of pre-college mathematics, and of course, elementary number theory by David Burton. And after that, we have a similar but challenging problem. So 2n ambassadors are invited to a banquet, and every ambassador has at most n-1 enemies. And they're asking us to prove that the ambassadors can be seated around a round table so that nobody sits next to an enemy. Again, it can be done by counting. So yeah, let me know if you're able to solve it or make any progress on it. Until then, I'll see you in the next video. Thank you very much. Bye-bye.
Cheenta programs are designed for students who are passionate about mathematics. And they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.